one of them is a Sun Devil, Mahesh here. So when was the last time you were here?
1992.
92. So
you guys are probably born at that time.
And then Mahesh Tirupatu is the executive VP of Analog Bits, and the presenter will be Alan Rogers. He's the president and CTO of the company, Analog Bits. The presentation will be as you've seen in the abstract. I'm not going to repeat it, but it's going to be some of the design trends in deep submicron, 28 nanometer and below SoC analog mixed signal building blocks. And Alan's background is in server class microprocessor, volume consumer semiconductors, and high reliability aerospace and defense applications, and he holds several patents. Mr. Rogers holds a Bachelor of Science degree in engineering from Imperial College in London. And Mahesh Tirupatu is responsible for business partnerships, IP licensing, and joint venture development. So if you have any ideas, you should go see him. If you need a job, I guess you need to go. He has helped lead Analog Bits to its position as the leader in integrated timing and interface IP, PLL, VLL, and whatnot. Prior to Analog Bits, Mahesh was holding an executive level position leading leading IP and library companies. He earned his MSEE degree from Arizona State and the business degree from UC Berkeley, but we won't hold it.
No, I like that. I like ASU. Cal Bernstein quite got it from me.
I'll leave the floor to our presenters. Thanks.
Okay, thank you. Hey guys, thanks for coming. We'll tell you a bit about our company, and we'll tell you a bit about the design challenges we meet. And if you find that interesting and do want a job, come and see us. First thing to notice is the logo. What's this all about? It's DRC clean. That means we can put this on chips. This is on 14 nanometer chips. It's in lots of other processes too. There's probably one in your pocket, one in your TV, one in your computer. So it goes on every chip that our IP goes onto. Never comes out the right colors though. I don't know why. Always seems to be gray when we look under the microscopes. So the kind of products we do. We're a mixed signal IP company, and one reason we want to come out and see people like you is to let you know that things like this still exist. It's not just logic companies in the world, logic and software. There are still companies where you could be a transistor level designer and make a difference. And you know, we've few of the performance metrics around here, things like 190 nanojoules of power consumption when you take measurements on sensors, 10 gigabits per second of I/O on cheap wire bond packages for consumer and other applications, 1 gigahertz T-cams, that's ternary cams where you actually look up and do comparisons at a 1 gigahertz rate. Lots and lots of really cool things we do. And you can do too if you know what transistors do. So we're going to tell you a bit about the trends and why things are changing, why so what Mahesh learnt 20 years ago doesn't 100% apply, and even what you're learning by the time you come out isn't going to be 100% apply. And there's other things you have to learn, and we'll tell you a little bit about that, a little bit about our company and technology, and a little bit about our design philosophy. So, some things change, but this is high technology, so change is normal. So get used to it. Everything I tell you will be out of date at some point. Key thing that happened at 28 nanometers is we got our high K gates. Most processes from now on are going to have a something big's going to have to happen. At 20 we went to double patterning. At 16 and 14 we went to FinFETs. At 10, we don't know, it might even be triple patterning. But we're getting to atomic scales, it's hard. Now, one thing is process variation. This isn't actually new. I remember in 2 micron days when we saw transistors that had fast and slow on the same transistor. Process variation is normal. If you had really good control of the process, you make all your transistors smaller. So by definition, if the process guys are doing their job, variation is normal. What varies now, because we are getting closer to atomic levels, is that everything's varying. It's not just 1 or 2 things, not just a channel length, not just a little bit of gate oxide. Everything's varying. For a long time, the example we mentioned up there has been true. VT's been coming down as a percentage of the power supply has been coming down faster than VT comes down. More and more electronics goes into low leakage devices, the phone in your pocket kind of thing, tablets, laptops. Leakage is the big killer. There are billions of transistors. If everyone just leaks a little bit, a billion times a little bit's a lot. So the VTs tend to go up and the power supplies tend to come down to keep power down. And for analog designers, this is hard. The voltage headroom with which we have to do anything is going away. Now that sounds bad, but really it's good, because if it wasn't hard, we wouldn't have a job, would we? Someone else would be doing it, and the old designs would work. So all this is good. But we do have to worry about that. We also have to worry about leakage as we try to get power down. Leakage is a percentage of the signal. It becomes a signal to noise issue. The way I have come to define analog is when you care about signal to noise, you're in an analog realm. Now that might be in an SRAM where the signal is a transistor that's turned on to show it's a 1 or a 0 against the leakage of the 100 transistors that are turned off or supposed to be off. It could be noise of a device, could be noise of a power supply. But signal to noise is what it always ends up with in almost everything we do. Another thing, large die, small geometry. Variation is more and more. Now, at least 28 was the last time when if you drew two transistors, they were made together and you get some moderate matching out of that. Now at 20 or 16 or 14, you draw two transistors, they're on different masks. So they're not sort of twins anymore, they're sort of siblings, sisters or brothers and sisters, even worse. Having sisters myself and kids, I know this thing. So there's an extra variation that we get. Another thing is power supply and power density. Above about 40 nanometer at say 65, 90, the temperature across a chip used to be pretty uniform. The heat spreaders could make it go. Every time we go down a generation, we double the number of transistors on a chip, the power density goes up. And what happens is we're getting local heating. So we get local heating and we get voltage variation. So we've got to worry about temperature and voltage are not necessarily the same anymore across a chip. Once again, this leads to opportunity. It means that we can sell people temperature sensors to put all around their chip. No one can really design a big chip nowadays. When we hired Mahesh 20 years ago or more to make microprocessors, a microprocessor filled a chip. Now, if you look at a big Intel microprocessor, I mentioned Intel because they've got the biggest design budget around, yeah? Look at one of their chips, it's mostly memory. Okay, that doesn't really count. You may design a memory cell and array it. And then what about the microprocessor? Well, of the space that's left, there's 8 or 12 of them arrayed on the chip. So sort of an eighth of a fraction of the chip is all you can design with the biggest budget in the world. So most chips are just arrays of things. When people say, you know, I made a big FPGA, I've made a big GPU, you know, they've just arrayed lots of little GPUs or lots of little FPGA blocks, and that's a big chip now. The advantage of this is now you can have software control. So if you have got some massive processing chip with 1,000 processors on it, you can see which one is the coolest using a thermometer, and you can send the workload there. And this matters because just 5 or 10 degrees can double the lifetimes of devices, and you know, as they're getting smaller, lifetimes becoming more and more important. As things are getting smaller, the other thing we have to worry about is that the metal, for instance, comes down in one dimension and the other dimension. And so electromigration is a real killer now. A lot of our designs, we start designing the metal first. When I was young, we'd draw a schematic, we'd do a layout, which, because of layout parasitics, might be 10 or 20% difference in speed, and then we'd ship the thing. Somewhere around 65 nanometer, the parasitics from the layout were dominating the speed of the transistors. Well proximity, stress effects because the devices were so small. So we'd do a schematic for functionality. We'd lay it out and then we'd simulate it because the speed on the schematic was irrelevant. At 28, we started with the metal because the hard thing is often how to feed enough metal into these devices. So we designed the metal power structure. That told us how big our transistors could be, and then we could go off and do our schematics. So it went metal layout schematics. You can do it the other way, but you end up iterating. You do the schematic, you do the layout, it's a different speed. You go back to the schematic again, you do the layout, and then you do the electromigration and find there's not enough metal, then you tear it all apart and you go around again. So we have to, anything high speed or high power density, we have to start at metal first. Power density. Okay, modern CMOS characteristics. Every process, something gets fixed and everything else gets worse. So, for instance, in 0.13 days, and just below that is where we first got copper for extra conductivity, and everything else got worse. The gate started leaking. At 28 nanometers, when we got high K dielectrics, the gate stopped leaking, but everything else kept leaking. The channels did. At FinFETs, the channels stopped leaking, but the drains and sources are still leaking, and it's all getting worse. Everything gets worse except the one thing they fixed, which once again is good. It means there's work for the boys. I appreciate that. Design for reliability. I'm sure your professors tell you this, and I'm sure you say boring. There's no great papers in reliability. You know, I can't prove something lasts for 1,000 years and then publish. I'll be an old person by then. But we have to design for it. The one thing that people want is that their chips work. Almost anything else can be forgiven. If you haven't got the fastest, you can still sell it. You know, if you haven't got the lowest power, you can still sell it. But if it doesn't work, you can't. And no one wants something unreliable. You know, if you have a phone that breaks, drop calls, or a computer or a car that randomly accelerates, no one wants that kind of stuff. Reliability is the number one thing. In analog, it's doubly hard. It's triply hard. That's what makes it fun. One thing is it's often very hard to test analog, so we have to think how in the middle of this big digital chip are we going to test our analog blocks. Another thing is the processes. At our company, we often work on advanced processes. People want the latest, greatest stuff. The trouble is the process models we get aren't for production silicon, therefore the experiment before production. Why? Because it's a new process, production hasn't started. So the process models are wrong. They're changing and will continue to change until the yield is good. And then in 5 years' time, it will be an old process and it will start changing again to get the cost down. So there's this continued cycle of change in which we don't want to intervene. We want to do one design and it will work forever. So often our designs, you might look at them and say they're primitive. You know, you could have done that in a day because you made it so simple. We made it so simple so it would always work. To know which simple to make it always work, but that's what takes the time. So we do things that will work whatever process is thrown at it. Simulations are used a lot, but it's for optimization. Challenges, we see large VT variations, differential circuits. We still use a few differential circuits, but we avoid them when we can. Back in the day, when you had bipolars, you could make really good differential circuits. CMOS, it's never been as good. We often have to for things like signals. If you send in a 10 gig signal a couple of feet, the electrical characteristics fall apart. We have to have differential, so we've got something to compare it against. We run into signal to noise issues again, but as much as we can, big swings are what we like. Signal to noise is good when you've got a big swing. And we've already mentioned about metal and lifetime issues. These things have to work forever. How are we doing on time, by the way, Mahesh? We're a little bit fast. Another problem, so you've made this design and you simulate it over corners, and perhaps you've got some corners from the fab and it works and it's great, but the processes age, and things have always had a lifetime limit, but it's just all getting worse. Too many more things raging now. So you have to worry about that, build in some extra margin for that. Process variation. One thing that's very helpful are Monte Carlo simulations. Basically, the simulator throws random deviation. Now, this can do some bits of help, but really you've got to go and search out failures. The job of a designer is not to design something that works. The job of the designer is to make something he thinks will work, but that's the easy task, and then beat it up to find all failure points and then design them out so the thing will never fail. And that is what a designer will spend most of their time doing in an interesting job, in what I call an interesting job. If you work in a library department of a big company characterized in NAND gates, you won't be doing that, yeah? But if you come to a leading edge company, that's what you're going to be doing. You'll be finding out every way the thing could fail and then design it out so that whatever the process throws at it, it will always work. As I mentioned before, as long as it works, people will want to buy it. And then in a digital environment, our customers aren't always the brightest analog engineers. Obviously, I mean, that's one of the reasons they come to us. Most of our customers are large digital chip companies, large digital chip groups, and we have to make things that are foolproof. In fact, we have to make them sabotage proof. A little story, you know, once upon a time, you know, the designers doing the analog would do, and the digital would all work together in one company. And then, say, 25 years ago, it kind of split off where you'd have specialty analog companies like ours doing analog parts, and we'd show the stuff to the customers and tell them what to do with it. Now it's changed. What happens is we go and explain how to use it. They send it to their design integrator, forgetting to mention any of our great wisdom. The design integrator sends it offshore, where there are some really smart people who are paid to ship a chip on time, and they will do anything they can to do that. And so they're working hard against anything you haven't thought of to get rid of any warning or error message to just ship the chip. So the complexity, anything subtle, has to be hidden and not just foolproof, it has to be sabotage proof. Moving on to FinFETs. Gate leakage was sorted out with high K, which started about 28. Channel leakage, the FinFETs do a great job by wrapping around the channel of getting the leakage down. Substrate leakage continues to go up at the bottom of the channel at the source and drain. So that's a problem. The other thing is the gates aren't as good as you might think, because you see pictures of these fins and nice even oxides or gate insulators around them. How do you grow a rectangular insulator? It's not that easy. So fins are almost never like you see them in the textbooks. They're almost never sort of rectangular. They're kind of curvy or something. And anyway, you've always got a weak point at the bends. So we have to worry about that. Quantization of transistors. We can't choose the width of a transistor anymore. We used to do it at any random grid. The grids in both directions are fixed. The fins are fixed in one direction and the gates are fixed in the other direction. Both are limited by wavelengths of light. So we're not only hitting atomic issues, we're hitting photolithographical issues. We cannot pattern these things. We're hitting the light, and as I said, most of this stuff now is double patterned, so it's half the wavelength of light and two different masks we're lining up. And then lastly, electromigration's got worse. When you turn the transistor on the side, you've got a lot more transistor in the surface area, but we didn't get a lot more metal. The metal's all got thinner too. So once again, electromigration's a killer for us. So summary, old methods of design don't work. New ways of doing the designs, doing things like starting metal first in the circuit design. And we architect the CMOS with the system in mind. It has to work, has to be reliable, has to be testable, can't have the integrator be able to goof it up. And we found that if you assume the transistor models you're given are wrong, you won't be disappointed. Because they probably are, because they're probably changing, and they will certainly change in the future. Okay, let's go in a bit about the specific products that we do. and a bit about the company. So the company's been around since '95. We're in Silicon Valley, and the big difference between us and most other IP companies, IP is intellectual property. We design and we sell effectively the rights to use a design. Is that we're an engineering company. We're full of CMOS engineers. Mahesh is really the only business guy, and he's an engineer, really. He was
ASU, it's kind of
ASU. I mean, this is the best engineer. Even our receptionist has an EE degree. So most IP companies have a few engineers, probably in Romania or something, and then they've got salesmen all over the world, which is good. They supply commodity IP and allow people to make chips. That leaves a niche, though, of an engineering-centric company that does all the fun stuff. That's what we do. So if you're interested in doing fun stuff, come to us. If you want a boring life in Romania, go to someone else. Core values, we work very closely with the customers, and we have customers all over the world, and some of the very biggest guys. Here's some pictures. We don't actually make many test chips, but at most new process nodes, the fab like us to run something. So there's a 20 nanometer one. 20 nanometer designs are actually in production now, and will be in your pockets later in the year. The 14 nanometer test chip is something we recently received. And we're doing 16, which is a very similar process soon, and working on 10. So the kinds of things we do, people want from us. They want clocking for their digital chip, all kinds of clocks, not just a logic clock. They'll want SerDes clocks, they want RF clocks, they want video clocks, lots of fun things. SerDes, basically serial differential data on and off a chip. The way to get the most data out through the fewest pins is SerDes. That's what we're really good at. And then generic interfaces, more conventional IOs. Sensors, temperature, voltage, process monitoring, and memories, especially high performance memories, people will come to us too. And so these are the kinds of products that we do. These are the transistor level designs that we will put on big digital chips, and industry-leading performance and lots of volume production, and probably in your home and or your pocket. A little history. Very early on, we did things like custom libraries for microprocessors. We did SerDes very early on. Got awards from IBM. And as the years go by, we do more and more interesting things. We finished at 2012, though. We need to update this slide.
I think there's another one.
There's another one, is there?
There's a little bullet which should come down there.
Wow, it's still out of date.
Yeah, 14.
So usually, there's 2 hours from California to Arizona. And usually Mahesh is there typing, and he's updating all the slides. So it's always a surprise when I come and present this to the students or customers.
Engineering problem, yes.
Yeah. This time he sat next to a pretty girl, and I don't have so much of an issue. Okay, and this is kind of how our business, our customers, which are all the big name people who make all the great stuff you like to buy. Then we have a customer-facing organization. So these are engineers doing support, writing logic models, library timing models, those sorts of things, doing some marketing. As engineers in our company, you can get onto show floors and show the products and meet customers. It's quite fun. And then we tend to be in teams, but these teams are pretty fluid. So if you're interested in lots of stuff, go to a small company anyway. As someone else mentioned, I think if you go to a big company, you tend to get pigeonholed in one place. We've both worked in big and small companies. The small ones are more fun. Sometimes people are scared of small ones because they're financially not sound. In our case, we've been around since '95, and while we've been in business, as we like to point out, Apple's looked closer to bankruptcy than we have, so don't worry about us. Here are some of the processes that we support. The reds are in production, and the blacks are in some level of pre-production silicon or design. Some of our customers, especially the bigger ones and the analog ones, are very sensitive about us putting our names up, so we don't. Those ones are at TSMC, and then we have many, many other fabs as well. Big companies, small companies, all over the world. Tell you more specifics about some of the products. Clocking IP, So every digital chip needs clocks, and someone needs to generate it, and that's what we do for all these kinds of products. A wide range PLL, we make something which is sort of solves 90% of the market, and you just put almost any frequency in and program it, and it'll spit out almost any frequency out, and that'll do for most logic clocks. And then people want high-end performance ones for analog applications, ultra-low jitter ones for high-end analog or high-end communication kind of applications. Very low power ones, if you think of something like a Bluetooth headset or a hearing aid your granny has. You know, it's got to work on a tiny battery for hours and hours and days. So we make things that will work at sort of 1 microwatt while they're working. And high reliability, if you're in an aeroplane or a satellite above the atmosphere, you get hit with a lot of radiation and it knocks stuff out. So high reliability is much appreciated by most airline pilots and anyone using satellites. Clocks are all over the place. We like to put up the old Xbox 360 because that had a chip which had 14 of our PLLs in it, millions of units shipped. And cameras, camcorders, FPGAs, all kinds of products these go into. Here's just a comparison. This is actually quite an old slide, but there were other companies that made PLLs, and that was their size, and that was ours. Ours is much smaller. It was then, it's still much smaller than theirs. Theirs aren't quite as bad. Is this the annotated slide where so see these guys here are both customers now. This fab is still in business, they're doing well. These guys went bust. These guys are still in business there. Our buddies down the street in Los Altos. And, but we're still the best. Been the best for years. So how do we make things which are basically smaller? And really we go back to first principles. What does this need to do? Most people make a mistake in analog design in a digital process, which is they say, well, these devices aren't matching, I'll size them up and make them bigger. It leads to all kinds of problems. Things go to hell. As soon as you double the area, you've doubled the charge that you're getting from the outside, you doubled the noise just to get the matching right. You really need to go to the other technique. Shrink everything down. If it's small, if you've got 100 millivolts of noise across a substrate, this much substrate, then you've got 10 millivolts, 1 millivolt, 100 microvolts. It goes. Just make things small as you can. Big swing. Do what the processors are good at. They're good at going fast. Try and clock things fast. Up to the electrical migration limits, of course. And that's the kind of thing we do. So this is what one of our PLLs look like. There's the actual PLL. These are the capacitors. We've built in a power supply ESD structure and all the digital logic with it so that people can shove this into a power supply ring. That's why it's a funny shape. And then they can just APR, automatic place and route, all the signals up there. Means anyone can use it. They can use a power pad. They can place a power pad. They can place one of those PLLs and then just let their tools run on it. This is the sabotage-proof level that you want for your designs, because if you don't, you'll give them a great PLL and they'll get the grounding wrong, they'll screw up the ESD structure, they won't be able to APR it, or slow their tape out, and the chip won't work because they did something wrong when it came back. So this is what you have to try and aim at. This is a kind of shrink-wrapped, analog all hidden inside kind of thing that will allow you to make chips that work first time. And if your chips don't work first time, you will be left on really old nodes where it's really cheap to respin them, and on no critical products. This is a PC graphics video card. We've done many generations of this. As you saw, our PLLs were very small. The nice thing about a PC graphics card is consumer magazines give a review. No other graphics card gave better image sharpness or color richness, which means that the PLLs were at least better than Intel's, Nvidia's, ATI's, for instance. So they're not only smaller, they're better. Here are some other PLLs we've made. This is interesting, fractional PLL. There's actually 2 PLLs, divider logic, a little DSP engine to allow spread spectrum. It's a line lock PLL. This is actually a digital data path, pseudo 3 gigahertz data path we made to calculate where to put clock edges. That goes into monitors, basically turning VGA into digital for LCD panels. That's a sub-microwatt PLL. It's a very low jitter PLL. Lots of people make LCPLLs. You can see the inductor here. But the performance they get out of it is usually really bad. Many of our competitors or people who have worked in the fields we worked in, they make LCPLLs and they get about the same performance as our ring oscillators. But we do use LCPLLs and we get incredibly low jitter numbers out of them, measured by customers, not just sort of a one-off test chip that we did. And it sounds obvious, but the devil is in the details. How do you make this work? What are the parasitics? The parasitics are what cost everything here. Work very hard on the design, the exact placement, the metal thicknesses, what metals to use. It's no good just being an electrical engineer and knowing what an inductor and a capacitor is and a transistor to make a good one of these. If you just know that, it's going to be horrid. You've really got to know the layout rules. You've got to understand the physics of what you're trying to do. Come up with grounding schemes. That's what's needed to get down to these kinds of performance levels. So one thing I'd encourage you, if you are doing circuit design and you want to do chip design, do try and do some layout in your course. It pays massive dividends throughout your career. Here's some silicon measurements of a PLL like that. These are random jitter numbers over a certain integration bandwidth. As we lower the PLL bandwidth, basically we get more noise from the PLL, and as we increase the bandwidth, it locks to the ref clock better, so you get less total jitter. I think there's some interesting annotations later, but these are sort of components that go into the jitter, such as the reference clock, the VCO, and the output stages. The output stages tend to affect the high frequencies. The reference clock affects the low frequencies. There's a middle. There's an interesting little bump there. I hope that gets annotated. Similar one, different bandwidth setting. And it tells you this little bump here is an interesting one. That's actually power supply coming through. It's leaking through. It's amplitude modulation from the power supply. SerDes. SerDes is the way of the future. Every generation we can get twice as much stuff on a chip, but we can't get twice as many pins in and out. So the chips run faster, they've got more things on them, but getting data in and out is a problem. SerDes is a cure for that. We get more data in and out of the same number of pins. We supply the lowest power SerDes, just like our PLLs were tiny, our SerDes are too. Whenever we show customers the power levels and the area, they say, does that include everything? Does it include the PLLs? Does it include this, that, the other? It's just unbelievable. So if you want to make the very best things like that, do come and talk to us. And they go into lots of products, FPGAs, consumer cables. Cables are really interesting. Cables used to be wires clad in plastic you plugged in two ends. They're not anymore. The really interesting thing at the Thunderbolt cables, which you may have heard of, was they actually have SerDes retransmitters in them. So from a protocol point of view, that Thunderbolt cable could be a long string and you send optical waves along it like children do, or it could be, you send sound waves along it, or it could be optical and you send light along it, or it could be twisted pair or coax or anything you like. But the plugs are actually active and they have SerDes retransmitters each end. And this gets around problems. If you remember USB, if you want to extend the cable, you've got to have special extenders and things. Doesn't happen anymore with Thunderbolt. You could have a mile long cable and it can be optical, or you could have an inch long, and it could be a cheap piece of twisted copper. And so SerDes, we've made them many years. Every year the processes get finer, the speeds get higher, the power goes down, except it's hit a bottom now. What happens is, as the speeds are getting faster, the budget, how much time we've got to do anything, gets smaller and smaller. So if you think of PCI Express Gen 3, which is available in some machines now, it's 8 gigabits per second. So we've got 125 picoseconds to do stuff, and the signal has degraded so much it's a closed eye at the end. So if you just look at it, there is no signal there. You can't see the signal. You've got to have special filters to actually get a signal out of it. And we've only got 125 picoseconds to start with. So You have to put more and more energy into the clock recovery units, the PLLs, basically to improve their fidelity. We have to, once again, it's a signal to noise fight. We have to get lots of signal for little noise without burning a lot of power. So that gets harder. So the power is starting to go up again as we get 10 gig, 12 gig, 16 gig, 28 gig, just to try and get this fidelity back. And here's some of the products which will use it. There's this is 16-lane PCI Express graphics card, supercomputers. Some SerDes companies will tell you their bit error rates and they're mathematically extrapolated. By going into supercomputers, we can actually measure them. So when we say measure bit error rate less than 10 to the minus 23, that's not an extrapolation, that's an actual measurement. Yeah, Mahesh bought his old computer because he knew he had a VGA cable on, but the new one, MacBook Air, has SSD controllers with our designs in it. Once again, very big customers, the biggest customers use our products because they're low power and really, really good. Thunderbolt cables, televisions. Television's very interesting. I used to think it's so sad. You know, I grew up in England, moved to America, and you know, we used to have TV factories and wasn't that great, high technology. And then over time it went off to the Far East, and I thought, oh, that's very sad. And now I go, I don't know what your electronics companies are, but we've got a place called Fry's where we go and look at all the goodies, and you can get a 40-inch TV for $300, and next year it's got to be 20% cheaper and UHD, and I think I'm so glad I'm not in that business. That's a killer business. But we can still help those guys out, make cheap TVs for everyone. And one thing is, when you had standard HD TV, they'd have LVDS going to the LCD panel from the motherboard. But when people want ultra high definition and 3D and 240 Hertz refresh rates, you've got a ton of data you've got to get there. The other thing is, of course, yeah, money matters because they're making these things by millions, yeah? So we have to get the silicon area down. Okay, and then, but really actually the bonding pads cost money, so actually going to SerDes helps get the data rate up, less pads, they love that. But then usually the package is more expensive than the silicon, so they want to get the power down, so we have to make a low power version. But then the ribbon cable which connected the chip between the motherboard and the panel was even more expensive. They used to use ribbon cable in the old days, and what do you know, they like it because it's cheap, and so they still do. So we're having to send SerDes data across those ribbon cables, and as they warm up, their characteristics change, so we have to have adaptive filters to compensate for that. So really fun business. And it's really fun working with guys like that. They're so aggressive. They have to come out on schedule. You know, Christmas or CS will come the same time every year, whether their products are there or not. So they're really aggressively fighting, and they have to get the cost down and the quality up every year. It's a great business to be in. And then here's some high-end networking stuff we go into as well. Here's a strip down of some chips. This is one of the old Apple chips in Samsung, 45 nanometer, and there's one of their SerDes marked. That was a 5 gig SerDes with 8B10B encoding, really easy encoding. Very similar process. There's one of our SerDes. You can see it's much, much smaller. But not only was it much smaller, it had a much harder job to do. It ran at over 10 gigabits per second, so twice the speed. Had a 6466 encoding, which means we're not guaranteed that any bits are going to change for a long, long time. Had spread spectrum. It had to work in a wire bond package, and it had to be low power because otherwise the plugs melt. So, you know, how much better are our products than other people's? It's that much better. They're smaller and faster and lower power, and all in a harder environment. Here's compliance patterns. I don't know how many of you have done lab work, but this is a nice little curve here. This kind of shows the jitter from our SerDes, and the triangle is kind of where we had to hit inside, so very comfortably inside. There's an FPGA test board with some of our SerDes on many of the protocols they tested it for. That's just a standard SerDes block diagram showing one side you have relatively wide buses of standard logic synchronous buses which go to the chip for APR. One side you have high frequency pins which come off the chip, and in the middle, shrink wrapped is all the stuff we make. We try and hide it as much as we can so they think it's just a pad that they have to place on their chip. So here's some pictures of it in layout, GDS. There's a wire bond version in 0.13, 19 nanometer flip chip. It's a 40 nanometer one. This is an interesting one. This is in a networking chip. So these are bumps for bonding out for flip chip. So you see the SerDes actually fits under a pair of bumps. Well, it needs at least 4 bumps, 2 for transmit, 2 for receive. So the SerDes is much smaller than the bumps. It's another interesting feature here are these inductors. They're very rare on the SerDes, but I'll tell you why they have it. Most times when you've got a SerDes, the pad, this big lump of metal here, plus the ESD structure, all have some capacitance, and really we want a pure 50 ohm line. So you'd like to add a bit of inductance to that. Well, when you come off chip, you go through a ball and you go through a via onto the substrate of the package. And at that point, if you open a hole in the ground plane around the via, it'll act like a small inductor and cancel out this capacitance. Well, that's good. These guys had something like 70 or 80 SerDes on their chip. If you do that, for 4 pins for every of those, every SerDes, you end up without a ground plane anymore. You just have like this big, all this cheese with all these holes in it everywhere. So what they did is for the lower frequency SerDes, they just brought it out and suffered the lack of inductance, and for the higher frequency ones, shoved a couple of inductors on chip to fix it. Just a table showing how much lower power and area than other people. This is a PCI Express Gen 3. So what's interesting at the higher frequencies, so before you saw the layout plots and you had a SerDes and a couple of PLLs receive and transmit, big capacitors are turning up. What's happening? This, as we mentioned, we're trying to get the random jitter from the PLLs down to get the quality up. 2 things we do. In the oscillator, we burn more power, and in the filter, we add more capacitor. And this helps us improve the signal to noise ratio. So that's the kind of trend as the frequencies go up that you'll see. Some 28 nanometer ones. 28 nanometer, as we mentioned and as we came into the talk, this was where high K gates were added to process nodes. But it's still evolving what people do with them. You've got, when it came out, it was a top end, so everyone making super duper stuff was in there. But still, people who are trying to get the power down on applications are moving in there. So this is a SerDes we did recently in a low power version of 28 nanometer, and that's going into SATA drives for video cameras. We also have a version that will soon be going into Wi-Fi units. And here's some dedicated transmitter and receivers. For a transmitter, you can use a single PLL, and this we have 4 transmitters either side. Receivers, we need separate PLLs for each one because we don't know the phase that the signals are arriving, so that helps you adjust the phase. And here's showing, this was for the TV panels, the area of an LVDS link in blue against the SerDes that can do the same data rate in red. Big silicon savings. So as I said, silicon was first issue, number of pins is second issue, power is third issue. The key issue though was the cable. Similar thing for the receiver. I/O products. We make a lot of interesting I/Os. We probably make more different kinds of I/Os than any company on the planet. And the reason is this. If someone's making a standard chip and they want standard I/Os, they go to a standard library and there it is. If it's not in that library, they're stuck and they come to us. So anything else that's interesting, they come to, it seems to end up in our plate. So we make lots and lots of wonderful different I/O products. I especially like things like low noise crystal pads. This allows people to bypass clock chips, and especially in high volume stuff, saves them a fortune. And then low power DDR, everything's going low power DDR nowadays. Even computers have got low power in, just because power density is a big issue, and plus battery life if it's a laptop. Crystalless oscillators are really good. This saves people even putting a crystal. You know, people have talked about the Internet of Things. Routine, if you go to a hotel, It's rare to get a key nowadays. You know, everything's an electronic lock. There's a computer in every door lock. You know, loads of computers in every car. So you don't want a separate crystal for each one. Every time you have to add a crystal, there's pins that can go wrong, there's costs, there's power. So people are going to crystalless oscillators on chip, and that's the kind of thing you see here. The other thing is security. If there's wires going onto a chip, someone can hack it, which is great fun. I know, I'm sure many of you here have fun like that. And it's famous in Silicon Valley lore. People like Steve Jobs would hack stuff, and we all do. So not Mahesh and me, we're very good people. We never hack anything. But clocks are one of the things, and building them on chip, it makes your chip secure. Lots of other specialty IOs we do. Sensors, I like sensors. Go into lots of products again, energy efficiency, and you know, basically confidential information, security on a chip. You know, it sounds boring. It's for old people with big servers in banks. It used to be. But now your mobile phone can access your bank account. How secure would you like that? Probably very secure, thank you, yes. So people are worrying about hacking. You know, hacking Xboxes used to be fun, and you know, you could, if you put in 1,000 hours of work, these really bright guys would be able to save themselves $30 on not having to buy CDs or something for it. And that was fun. It's not so funny when it comes to stealing people's money, so we're all much more interested in making secure chips, secure systems that can't be hacked. Voltage manipulation and clock manipulation are great things. I'm not trying to give you ideas. But favourite things, stopping clocks so licenses aren't there, making them go fast and wrapping round. Voltage manipulation, you bring down the power on a chip, reset it, so that parts of it reset, and the parts that have all the keys to whatever don't reset, so when you power it up again, you've got the keys to the game, the bank, the whatever. So we can make sensors, things that will do things like, we'll have crystallis oscillators that can validate external clocks, make sure they're the right frequency. They can supply internal security things. They can check, they can basically have internal calendars to see when the thing was last reset. You can check the voltage from all around the chip with voltage detectors. Lots of fun things we can make these systems more secure. And there's just a picture of some and a picture of more of them. I really like these things, the sensors. These are a bunch of bipolars for a band gap that we put in. With something like a thermometer, to make it accurate to about a degree, we need to be able to measure 100 microvolts kinds of precision. And that'll be on a noisy chip where things are banging plus or minus 1, well, 0 to 1 volt. And then we have to measure 100 microvolts or better. So this is real analog stuff, and this is fun. More of the same things in different processes. Some examples of the output versus code, and these can be read by the machines on, and usually for temperature, as we've mentioned before, it's for reliability. They'll send the workload to whatever's quiet, or they'll shut down a system if it gets in too hot. It used to be that people would have a thermal diode on a chip and external thermometer chips, but obviously as stuff gets smaller and smaller, this is an obvious thing that we can integrate as long as we got designers who can design stuff with 100 microvolts resolution. And then we get spec test chips on things and we measure them. So in this case, we've got a couple of directions of VDD that we're varying, and then we're seeing how that affects the sigma, the random deviation of measurements. And in this case, it's very good. There's very little variation with voltage. And some more silicon measurements out of these things. So that's a summary of the sensors and the security level. Basically, how we can use these subsystems to make even things like mobile phones safe from hackers. Actually, I went to a security conference last year. It was very interesting. When we talk about people doing bad things, we call it hackers. Apparently, when the government does it, it's forensic data analysis. So, interesting. thing. So when you're talking to someone you don't know at Starbucks about your forensic data analysis, okay, everyone will assume you're the good guys. And there are just some of the different ways we make these subsystems. Memories, ternary cams and multi-port memories are kind of what we do. Networking guys and high-end processor guys ask us to do this. And the main reason I like showing it is we've made 30 million transistor macros at 1 gigahertz per second. It's just fun stuff. And it's not bad for an analog company to make a 30 million transistor block. So we like to show off about that kind of thing.
You should design 2 million chips.
Okay, so you know, what makes the product successful, what makes the company successful, what makes all our engineers successful. We make differentiated IP. We make stuff that's different that people want to buy, and we make a huge number of it, and our things work. And that's why customers come back to us. That's why the biggest companies in the world are our customers, because we make stuff that works first time. We've got customers all over the world in all kinds of processes, and we're engineering centric. It's an engineering company. It's not a marketing company. We have no glossy brochures to hand out. We just don't do that sort of thing. What would, if you were thinking of joining, what would make successful? What makes a successful candidate against a non-successful one? You've got to have a passion for it. You've got to really want to do this thing. We are at the leading edge. We are doing new stuff. You've got to enjoy investigating that and doing it and beating up a problem until it will always work. If you don't enjoy it, it will just be too hard work. It's just too much slog. You've really got to enjoy that. Definitively, you've got to be bright. You're at ASU. We know you're all bright, so that's not a problem. Understanding the basics. This is key. We have to try and make systems as simple as we can because they mustn't go wrong. You know, we're making a few transistors in a billion transistor chip for customers who are putting out products with billions of dollars of revenue attached. These things have got to be made and they mustn't go wrong even if the process changes. So you've got to understand the basics of what's going on. Effort and team player. The days when one person could sit with his soldering iron and make a really cool circuit are gone, I'm afraid. We're a team. Even if you're just a pure circuit designer, you've got to work with layout guys, you've got to work with modeling guys for the Verilog and library models and other things. So a team player has to be, you need that to succeed. But we'll train you. We don't expect you to know all the technology. Definitively, you will not know all the technology. The nature of high technology is always changing. If you've learned something at a course here, your professor wrote that course before you started it, he had to find it out from somewhere, it's guaranteed to be a few years old. We understand that, but we've also found that students or people straight out of college are really good at learning. So instead of sitting you in a room and telling you to think about a NAND gate for 10 years, we put you on the front line and we give you all the data. So, you know, we've got, Amit came from here. When did he join us?
He joined us about, I think, 3 months ago.
3 months ago? Yeah, he's already working on SerDes.
FinFET soon.
Doing some key work. He'll be on FinFET soon. Yeah. So very quickly, people come up and they're doing leading edge products for top companies. And why should you join? You know, we've got the energy of a startup. We are a small company. I'm the president. Mahesh is the executive vice president. So it's a fun place. You can get a lot done, but it's not shaky. It's not like half pay and perhaps some stock options. It's good money. You'll get to do real work very quickly. For big companies, you'll be able to walk into a store in a year, and the chances are there'll be at least one product there that you've put some design work into. FinFETs getting more and more important. Whatever the high-end process is, you'll be on that, and you'll be working with a best-in-class CMOS team. And in many places, so when I hired Mahesh out of ASU, I was at Sun Microsystems, and it was a great company when it was young. We could get a lot done, but the truth was, circuit designers were a cost center for them. It wasn't where the money was made. It wasn't the glamour. We thought it was an important job. I'm not sure the rest of the company did. But now we work at a circuit design company. If you come work with us, you won't be a cost center. You're the revenue center. You are the key of the company. So there's more glory to go around, I guess, is the point. Is that the last slide?
Yeah, I think that's the last. There's one animated slide which I like.
Whoa, what's this?
This is a cool slide which I thought I could show it. And this is true. Blue is if you work at Qualcomm, Broadcom, or Microchip.
Some other commie company.
Red is when you work at Analog Bits. Right? What do you guys want? You want to put out great products and get paid well for it, right? Who doesn't want that? And then you should be in. I'm glad I didn't see any hands. I told you to go work in, in a non-profit organization. But the point is, this is important. This is a very important fix that we give to our students. Is what you are doing is relevant and it matters and people care and people make money out of it. So, and as an engineer, that's the most gratifying experience. Alan says, well, I went to the dark side and went to sales and marketing, but the job is very technical. I have to interface to the CTOs and VPs of engineering because they got killer products on the line. And as Alan said, CES doesn't move, MWC doesn't move, Christmas doesn't move. They got to get a product out, and they come to us, these high-intensity projects that we take on, and we make them successful. So no glory, no guts, no glory. So it is indeed a great position. And for you guys, what it is you actually are at the forefront of technology. You're sort of the Marines of the business. We go in first. Many of the IP companies come afterthought. So what that is you get to work on some of the most leading edge stuff, which makes a big difference. Now, how many of you want to be designed in the latest iPhone or Galaxy? How many of you want to be designed into a microcontroller after 3 years, which is going into a garage door opener? So that's what you might be doing in other companies. So
actually, we do that too, but
but that's the point, is you're working with a real engineering team. How many of you want to be the president of a company someday? There you go. How many of you want EVP job? Well, that goes first, by the way. All jobs are...
No. President goes first. We need a good president so I can go on the beach. One of you guys can do my work.
Exactly. But the point here also is you could be in a large corporation working in Broadcom or Qualcomm where you have hierarchies and silos of management. You don't see that here. What you're doing matters and impacts the real top line and bottom line of the company. So what it means for you is the engineering work that you put in has immediate ROI, return of engineering that you see. And that's important because that's important as an engineer. At Sun, I used to strive to be a marketing guy, trying to talk to all the shiny suits guys. They never used to tell us anything. Here, yesterday I come back from Korea, the engineers want to know what's going on in the market. And we sit and chat over a cup of coffee about this. But that's knowledge. That's immediate market-centric knowledge that you guys will have. And being an engineer at heart, it helps me translate that value proposition, what great engineers produce, translate it to bigger value for a customer. So they pay us well and we all get rich.
Yeah. Any questions? Yes.
There you go. Lovely.
So you mentioned 14 FinFET, 16 FinFET. I was wondering for your SerDes IP, what speeds were you? Is that information you can say?
Yeah. Yeah. I don't know. It died.
On the side, I think.
Oh, there's a quiz and there's a giveaway.
Oh, you have to take all the presents. Yeah, so our current SerDes run up to about 12.5 gig. There's still questions about whether we want to run 28 gig or not. But we are currently doing designs for 28 gig, but they probably won't be in the market this year. Yeah.
Your flyer had 14 gigahertz PLLs. That was for...
We've done PLLs for other people's. So there are other analog companies out there with a 28 gig SerDes that has our heart beating inside it.
Okay.
Yeah.
So with the, I guess the following was with the EM issues that you found with FinFET, while you have to account and to meet electron migration rules, how do you still keep access speeds?
Yeah, that gets...
That you're adding now to your wires.
Yeah. Yeah, it gets very difficult. There are often rules that allow us, if the lines are short, to shove more current down it. The electromigration issue generally is not the famous one where a line gets thinner and thinner because the metal's moved away and then goes bang like a fuse. The issue is when it gets thinner and thinner, all that metal went somewhere, and where it went, the pressure increases and it cracks the dielectric open, and it spews through like toothpaste and causes a short. So often for shorter wires we get away with that. So indeed our biggest problem is designing the metals to feed these devices.
Yeah, but you have to meet the rules.
We have to meet the rules, yeah. So the rules are kind to us if we make them small, and then we power fewer devices, or for a same load we will have more transistors there, so we can add devices, so that each one takes half the load, you put twice as many transistors there. So there are things we can do. We haven't hit a physical limit yet, but we're having to put a lot more engineering into stuff that we never used to have to think about. Yeah. Yes, sorry. Yeah.
Go ahead. In digital design, we never actually treat length as a design norm, usually, but in analog design, we are both width and length as a design norm. So how much does it, put a constraint on the use of 3D MOSFET like FinFET, because the process is pretty much difficult?
Yeah. So in theory, we can increase the length of a FinFET. So if we use in a high voltage FinFET, the range that you can increase it is often very small. So we end up just putting a load of them in series. So it's not a very useful variable. The trouble is if you do put a truly long channel length, which you could theoretically do, you get into mechanical stress issues and you end up squeezing the devices and they don't match very well. So you end up breaking them up into lots of little units anyway. So you might see in some design rules it's coded that you can only have, say, from 0.16 to 0.2 microns, like you've got 20% variation channel lengths. Other processes, they'll let you do it, but then when you come to simulate it, you find out you wish you hadn't done it because the variation went up when you did it.
Thank you so much.
So it is it's a problem for us, but problems are good because, like we said earlier, if it wasn't hard, we wouldn't have jobs and get paid a lot for it. So we like it, yeah. Madam.
I have a question more related, I guess, to students. So it seems like you guys are presenting what you do, which is great, but also looking for potential hires.
Yes.
So one is, are you guys hiring right now?
Yes.
Yes.
And two is, do you hire new grads quite often?
Yes.
Yes.
Okay. And then three is, are you accepting resumes today, this week? Do you guys join the ASU Career Fair?
No,
do you do
we haven't.
Those things?
Oh, you should have got invited for that.
So, because I see a lot of students here are what we call digital or analog circuit students. So they might be interested in what you do.
Yes.
I am an RF circuits. I teach the RF circuits course here. And I often get the question, well, I'm a digital guy. Why should I take RF design? So when you are looking at somebody's background coursework, do you consider high frequency
Absolutely.
design? I mean, you're designing 4.5 gigabit per second thing.
Yeah, it's reasonably high frequency. Yeah.
Would you guys consider that more, being a high-speed digital person, are you more of an RF designer than you are a digital designer, if you want to look at it that way? Do you consider line lengths? You consider
It's always kind of been that way. Even at 100 megahertz, it was RF once. And certainly when you consider the SerDes, the signal integrity, get in the we saw things like inductors on the chip, or we on the package substrate. We make space around the vias to get the inductance up. All those RF techniques are important to us, although it's not what RF engineers call RF design, but it's many of the same things. It does matter, yeah.
Including your transmission line models for the channels and stuff.
Yeah, absolutely. We model transmission lines. That's the easy bit. It's always the connectors, it's the interfaces that really screw us up. Yeah.
In the transmission line modeling, we do use tools like AMI, use security and cadence tools. And we actually have to model it for the entire customer because they're driving high speed.
Yeah, I'm just saying there's a big overlap with
there is yes. There always has been. Even 25 years ago, making standard parts, inductance of packages mattered, and the frequencies mattered, reflections mattered. Early CMOS standard logic would latch up because it'd send out a 5-volt signal and reflect and come back as 10 volts and cause latch up. So all the things that RF people do have always mattered to us.
So I've got one last question, then I got to pop out. Is there a minimum list of requirements in terms of coursework, design experience that you guys have that you could send out to students that are interested, so that you're not getting inundated with emails and resumes that don't match?
Yeah, so there is no real minimum requirement. If people understand Ohm's law and what a MOS transistor is, we're interested.
Current law, KCL, KVL.
Yeah, so basics matter. After that, it's a passion. Now, if you've not done any circuit courses, I think we're going to think you probably weren't interested. If you did circuit courses and got Fs, we're probably not going to call you in for an interview. But you know, we're not going to say you haven't done our favorite course. We still think you should do RF courses.
No, don't do that.
Yeah, no, but there is no really minimum requirement. If people are interested, passionate, want to learn, and know the basics, you're in, guys.
So just to give you an idea of what I studied at ASU, though I was doing power engineering as a major because I was well funded for an RA. And at that time, 1990, ELSI had no money, so I probably you had great professors and great reputation. But the point was, I took every circuit class which was possible. Device physics, VLSI design, Professor Chaitali, she was just started that year. You know, VHDL design. But the point is, if you guys are going to be circuit designers, have RF course, have digital converter course, have device physics course, because it's important for you guys to see everything. Transmission line modeling. I mean, these are all very, very relevant courses. You might not use that very same thing, but you got the principles, and then people talk the lingua franca, you're immediately able to pick it up. And I think that's very, very important. The reason we're not an RF IP company is because most of RF tends to be within a certain client environment, and they're very protective and they don't want to release it. So for us, we're sort of serving a mainstream market where there's big digital SoCs, and the complexity that we deal with is in like 14 FinFET. The RF guys are still sitting in 65, slowly moving to 48 and 40 and 28. So there is a sort of a transition on the market. But we do supply people RF clocks, as Alan was pointing out. They build a Bluetooth or a wireless subsystem. They want a clock, a clean clock, and we supply such macros as well.
I think there's lots of relevant
absolutely. There's
students and coursework here.
Yeah,
for you guys.
absolutely.
So hopefully you find some good employees.
Great, thank you.
Yes, sir.
You talked about a time sharing issue at high, gigahertz rate, 100 gigahertz law stuff is getting pushed because of serial, and now they're trying to do even fiber optic cable, like on-chip fiber I/O. If it's too expensive to do that, or processing doesn't allow it, do you see maybe parallel coming back?
No.
No, it's dying. In fact, even the memory guys today, if they had a choice of going serial, they will go serial. Think of it as like a 10-lane highway versus a 2-lane highway. And
no, I understand that, but I mean, once you hit a limit of time sharing, then what do you do from there?
You can multiplex and get the data in.
Yeah, so if you look at DDR nowadays, I think 1866 is kind of the production limit. SerDes, there's 28 gig SerDes out there. Now the DDR, obviously you only use one wire for that, and the SerDes use 2 wires, but it's still like a 10x. And obviously they're working on faster DDRs, but they're working on 50 gig SerDes as well. So there's a significant factor in there. And the DDR cannot send that data the same kind of length that the SerDes can, because they've lost the differential information. It's a signal to noise compared to the local power supplies, which SerDes does not have that issue. Yeah.
Parallel that in the consumer market, it all used to be LVDS.
Yeah.
Right? I mean, your display used to be driven by an LVDS. Now you want 4K on your iPhone, right? I mean, high resolution's coming up. And you got to keep it in a small form factor. And you got to lower the power. You put all those variables in there, serial. It's just
Yeah, and power is a big issue in that DDR. All those DDRs were terminated lines, and you had to pay the termination power on every single one. It gets expensive.
You can kind of do a hybrid of that. You do multi-level signal downforwards and... You
can.
Yeah.
And people typically don't, and it runs into a signal to noise issue. Yeah.
I don't know if anybody...
No. The very first SerDes we did there in the 0.18 days was actually a simultaneous bidirectional. We sent signals both ways down the same SerDes. That was called Intel Standard Protocol. I think they only used it for one generation for one of their titanium, not titanium. Titanium.
It was a titanium anyway.
It was a Titanic. One of their titanium chipsets, yeah. So you know, we have done some fancy stuff, but there's just too many problems. Yeah. Yes.
In one of the PLLs, you expect the power with respect to, per megahertz, which is not the conventional absolute power spec. So, what is the basic reason behind it? You're expecting the power as 1 microwatts per megahertz. So,
yeah, microwatts per gigahertz, because it's a metric by which you can compare two things together. Because if someone says, you know, they're burning 10 milliwatts, but they're running at 10 gigabits per second, against someone who says, well, mine's only 1 milliwatt, but they're only running at 10 bits per second, you know, it can be misleading if you just quote the power. So milliwatts per gigabit per second is one metric, or nanojoules per bit is the other metric people commonly use. So you get a much better, you know, truth in disclosure kind of thing.
Yeah, we've got a little quiz here. Who's ready for a quiz? You do want to make sure you pay attention. So what's the most advanced technology analog bits is taped out? 14 there.
Yeah, don't throw the mugs. You can throw the dongles, don't throw the mugs. You got the mug.
Oh, who gave the second answer? Who's on memory stick? You see the trophy as the second prize? Somebody said 14? There you go. All right. How many offshore design centers do we have? 50. 50. Yeah. How many centers in Romania, how many centers in China, and how many centers in India? Zero.
Who said zero?
Organically grown California company. Well, Arizona too.
Mug. Who gets a mug?
All right.
There you go.
What is the difference between analog bits and other companies?
Many answers here.
Growth. Okay, growth is an answer. Coffee mug for some person who said growth.
More innovation.
More engineers. Who said more engineers?
Yeah.
Who said more engineers? That is the right answer. We're not a sales and marketing company.
But we do have these very nice mugs.
Okay. Give the best reason you will want to join analog bits. Besides Alan. Passion. Who said passion? Oh, there's a couple of right answers. Okay. Besides passion, what else? What's that?
You might want to design in less than a year.
There you go. Can you catch it? You want to throw it? I don't want to hit the...
You can design, you can be in many other streams also.
There you go. That's a very important thing, guys. Working in leading edge. Right? There are not many companies who will allow you to touch FinFETs. They'll say, no, you don't have enough gray hair. You don't have enough this hair. You don't have 20 years of resume. Where's your patent portfolio? Show me your PhD. Show me your GPA. You're not the professor's favorite. No. Here in our place, you were. Here. Got it? Oops. I sucked in cricket. Okay, one more answer.
You can work in various kinds of products.
Okay, that's good. So you get to work on multiple products. More than one product. Oh, sorry, I wouldn't break it. If it broke, it's probably our IP, our competitor's IP. Well, by the way, did you all enjoy the presentation?
Yes.
Yeah. What else would you like to hear next time? the good parties we throw. But by the way, that is an important attribute. If you do join Analog Bits, all the engineers will come and tell you one thing. They drink the best wine, eat in the best restaurant. And I'll tell you this story. When I was an engineer, that was the biggest fantasy for me. My God, I could be a marketing guy. I could go in, wine and dine the customer, have the best food and the best wine. Well, in the Analog Bits, everybody gets to do that. He equated that. So, any other topics that you guys would like to see next time? Maybe next time we should go to a coffee plantation and open a bar, and have one of those evening get-togethers and invite some of our engineers over. Well, do send resumes who are close to graduating. I think we're starting to hire right away, and so some of you might have gone through a phone screen. I apologize if we didn't get back to you, but certainly there's a lot of interest in hiring more people. As you know what the company is all about, you know what we're looking for. We want you to come and join the team. All right? Thank you.